Agenda. In this short video, I'll discuss the following topics. Topic number 1. A. The difference between bivariate and binomial. B. Review some basic concept and related formula for combinations. Topic number 2. Binomial distribution. Topic number 3. Poisson distribution. What is the difference between bivariate and binomial? Bivariate. Bivariate, for this course, it is for two variables, and we study their relationship. For example, we have two columns x and columns y. We estimate their covariance and correlation, or correlation coefficient. Another example, we have return of two companies, IBM and Walmart, in the last 10 years. And we want to look at their covariance and correlation. Basic idea is we want to know how strongly they correlate with each other. Binomial. For the binomial, we have one experiment, has only two outcomes. If we repeat the same experiment many times, what might be different outcome or combinations? A. We have fair coin. It indicates we have 50% chance for head and also for tail. If we flip 3 times, what might be the probability for various combinations? For example, head, head, head. And we know the probability is 50% times 50% times 50%. How about head, 1 head, 2 tail, or 2 tail, 1 head? We study the different possible outcome or probability. B. One investment has a successful rate of P, and the failure rate will be complement of P, 1 minus P. If we retry this investment n time, what might be its probability distribution? Let's review the basic concept of combinations. Order does not matter. We choose R objects from N. So from R from N. Order does not matter. Assume we choose 2 values from 3 values, 1, 2, 3. One possible outcome is 1, 2. Another possible outcome is 2, 1. Because order does not matter, so we choose 1, 2 or 2, 1 at same choice. B. Formula for combination. And the textbook use capital N, small n. We think it's better use N, capital N, and small r. Okay, so we choose R from N objects. The total unique choices is N factorial divided by R factorial times N minus R factorial. C. The Excel related function is COM BIN. COM BIN with 2 input variables. Next, we are going to Excel to show how to use this Excel function. Now, let's look at how to use an Excel function to calculate combination. And there are two input variables. One is small r and another is capital N. Okay. Suppose we choose two values out of 3. Okay, so what is combination? Okay, what is combination? Okay, and so we can use the function. Let's make it bigger. We can use equal COM/BIN. Okay, the first one is total. So total, and how many chosen? So it's 2. Okay, so in total we have. So in total we have 3. Okay, in total we have 3, and another way is we can just manually calculate. Okay, so this is the first one is factorial of n divided by, okay, factorial n, then factorial r, and divided by factorial n minus r. Okay. Now we have same result. Okay, I'm going to use show formula to show this, to show the formula of these two function. Okay, the first one is equal COM/BIN. The first input is total. The second one is how many we choose from total. Okay, and so copy paste. Okay, the second one we simply apply this function. Okay, apply this function. Okay, so let's randomly pick some value. Okay, 2 out of 5, and 3 out of 6, and 4 out of 7, and 5 out of 10. Okay, then we can simply apply the formula. So equal COM/BIN. Okay, the first one is big number, then r. First one is n, second one is r. Okay, so in total we have 10. Then we can use show formula. Show formula to show the formula of this. How do we get number 10? Then we can simply copy and paste. Then we have all the result. So this is a simple review how to apply equal COM/BIN Excel function to calculate combinations. Here is a simple example about binomial distribution. Okay. So what is binomial distribution? It's one experiment or one action operation. We have two possible outcomes. If we try n out, if we have n trial, what is the probability like r of them are successful or not? Okay, and here I use a coin. Let's flip a coin. Okay, so we flip once, we flip second time, we flip third time. Okay, suppose we have coin, and so this coin is a biased. Okay, we have 30% probability head. Okay, so this is 30%, and so we have a biased. So we have biased coin. Okay, and we have 30% probability to see a head, and we have 70%
probability to see a tail. Okay, so this is our probability. And you can call it success rate, or you can simply call it P. So this is a probability. Okay, and so this is our formula. We are going to use 3 ways to calculate. Okay, the first one is common sense. It's common sense. Okay, so let's look at the probability. Okay, probability we see head, head, and head. So we see head, head. Okay, we see 3 head without looking at this formula, without looking at Excel function. We just use common sense. So if we see head, 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 okay, what is probability? So we know that 30% we see one head. If we have another exact same probability jointly, and see this one third time. Okay, so actually it's 30% times 30% times 30%. So this is our probability. I repeat. Okay, suppose we flip a coin 3 times. What is the probability we see 3 heads? And we know for each of them is 30%. So 30% times 30% times 30%. So let's look at the T. So we T tail and tail. And what is probability with sweep tail? Because we know it's 30% head and 70% tail. So 70% times 70% times 70%. So actually it's 1 minus P. So 1 minus P, the power is 3. Okay, I'm going to use show formula. So this is show formula. So this is the G1 times G1. So this is probability power of 3. So this is 1 minus P power of 3. Okay. And so actually we can apply this formula to calculate. Okay. So this is, we have N, and this is kind of X or R. Okay. Okay. So this is X. R. Okay. So we try 3 times and we see 3 successful. And we try 3 times and we see 0 successful. Okay, I'm going to center this way. Okay, I'm explaining the concept here. So eventually we see 3, 2 and 3, 1. Okay, so we flip coins. So this is number of trial. So this is how many times we flip the coin. So this is number of success. Number of success. Okay, and in this case, our number of H. So how many H we are going to see head? So how many head we are going to see? Okay, and so if we use this formula, so this is equals. So this is N. So equals N factorial N divided by R factorial R divided by factorial N minus X times probability P. Okay, P. How many successful it is? times 1 minus p. So 1 minus p, the power is n minus r. Okay, then we have same value. Okay, I know this is a crazy formula. Okay, so this is very, very crazy formula. Okay. Actually, we have a much easier method to calculate. Okay, so this is by this is a binomial distribution. Okay, BINOM dot DIST, and the first one is our how many success, okay, comma. The second one is total trial, okay, and third input is our probability, and the last one is probability. It's not cumulative, fourth. Okay, then we have same result. Okay, I'm going to red one and red one and red one. Again, I'm going to show formula. So this is the formula. Okay, I repeat the basic concept. Okay, so this is binomial distribution. Okay, we flip a coin 3 times. Okay, and so this is Bi's coin. In 30%, we are going to see a head. 70% we see a tail. Okay, directly we know head will be 2.7%. Why equal 2.7%? Because 30% times 30% times 30%. Okay. Alternatively, for the 3 tail, and it's 34.3%. Why? Because it's 70% times 70% times 70%. And the second way to calculate, we apply the formula directly. Okay. Factorial n divided by how many success, and total trial minus success, and the p of success 1 minus p, and trial minus number of successes. Okay, and we can simply copy and paste this one. Okay, before we copy and paste, we have to fix probability. Okay, G1, so we fix G1. Okay, so this is $G $1. So we copy and paste. Okay, and the total summation should be 1. So let's verify summation equals 1. Okay, equals 1. Okay, and again, here I explain the concept here. Okay, so this concept is, so let's randomly choose this one to explain. Okay, we flip a coin 3 times. What is the probability? We see 2 heads. Okay, because the probability if see 1 head is 30%, because each flip is independent from other flips. Okay, and then we can apply this formula. The Excel function is simply binom dot dist. The first input will be number of success, like 3, 0, 2, 1. The second input is how many trial, and third input is probability, and the last input is false. Okay, question. Suppose this is a fair coin. It's 50% head and 50% tail without calculation. What is this number? Should it increase or decrease? This number, increase, decrease. Okay, so without calculation, we know this is 30 times 30 times 30. So if we change from 30% to 50%, this one should be higher and this one should be smaller. So let's just copy their value here. their value here. And it is also true. So let's copy this value here. Okay, so if we increase from 30% to 50%, we expect this value increase, this value decrease. Okay, and also we should know what is probability corresponding to these 4. Okay, so let's change it to 50%. Okay, obviously 12.5%, 12.5%. Head, will have same probability as tail, tail, tail. Okay, so these two values should be same, and also these two should be same as well, because now we have a fair coin. We have fair coins. Okay, so this will be quite different from these 4 numbers. Okay, so this is a simple example about binomial distribution. I'm using this example, I try to help you to understand the 2 things. First one, how can I apply this formula? The second is how to use binom.dist Excel function. Next, from the previous video, we know, suppose we have a biased coin. If we flip, so let's use some numbers. Okay, suppose we know n equals 3, and suppose this is x or success. Okay, success is 2. Okay, this is 2. So number of trial is 3. So the probability is 30% and false. Okay, so we got this number. Okay, I'm going to use show formula to see this one. Okay, make it bigger. Okay. So what is the meaning of this 18.9%? So this is 18.9%. Suppose we flip a coin, we have 30% chance to see a head and 70% chance to see a tail. Okay, and the probability we see 2 head is about 18.9%. Okay, for this exercise, I'm trying to use how can we use random numbers. We generate 5,000 random numbers, 5,000 times 3 random numbers to verify these proportions. Okay, so this is, suppose we generate one random number between 0 and 1, another random number between 0 and 1. We generate 3 random numbers. So let's try, suppose it's 0.1, so 0.2, and 0.45, and 0.55. Okay, suppose we generate 3 random numbers between 0 and 1. Okay, so this is success. Success 1, success 2, and success 3. Okay. Okay, because we know it's a 30%, so this is, we can say, hey, if this number is less than or equal to our probability, we call it success. Otherwise, we call a failure. Okay, because it's 20%, 0.2 less than 0.3, so this is a success. Okay. Before we copy paste, so let's fix it as F4. Okay, then we just copy and paste. Okay, because this number is less than 30% and it's success. If it's above 30%, then it's a failure, right? It's failure. Okay, so this is our summation will be 1. So if we try once, we flip a coin 3 times, so this 1, 0, 0. Okay. Okay, and obviously there's no way we can do this like 5,000 times. Okay, so let's generate 5,000 times 3 random numbers. Okay, so click data, click data analysis. Okay, data analysis, click random number generation, click OK. Okay, because we are going to generate 3, we are going to generate 3 columns. Okay, suppose we generate 5,000. We are going to generate 5,000. So this suggests we try 5,000 times. So each time we flip coin, this byte coin 3 times. Okay, and we from uniform from 0 to 1, and we use 1, 2, 3, 4, 5. As I mentioned before, if we use the same random seeds, we will get the same set of random numbers. Okay, so let's output on the same spreadsheet. So let's put it here. Okay, click OK. Because I enter some value here, okay, just override, click OK. Okay, so this is my generated numbers. Okay, I know some students they don't like, so let's use Control N. This is the value here, it's 5,001. Okay, 5,001. Okay, one way to do it is we can simply hide. So this is, I should hide some row. Okay, highlight several rows completely, then hit Control Shift down arrow. Okay, just keep the Shift key down, then right click, click hide. Okay, so this is our small data set. It's even we know it's 5,000 here, 5,001. Then we can suppose we can count. Okay, count. We can count how many values. Okay, it will show us 5,000, right? And so this is 1 because it's less than 30%, 100. Oh, same thing as before. Okay, so I copy and paste, then I just drag it down. Okay, I drag it down. Okay, then so this is will be summation. Okay, equals sum. Okay, so this is summation will be these 3 value. So obviously this is 1, 1, and we can copy and paste. Okay, so this is 1, this is 1, so this is 3. Okay, and how many, because we care about 2, right? 2 success. Okay, so not here. Okay, we can read. Okay, so let's look at count if. Okay, count if. Okay, so we are going to count this column if their value equals 2. So let's count how many. Okay, total there are 334. Okay, 334. Okay, so what is probability? So this is number of success. So this is count. And so finally we have probability. Okay, we have probability. So this is this one divided by total. Okay, so this is So this is our value. So it's 18.7%, so this is 18.9%. Because we try 5,000. Okay, so let's try another number. Okay, so let's try 3. 3 out of 3, and so this is equal binomial distribution. So 3, and 3%, and 4th. And we know is 2.7%. Okay, and so we can log. So G2, 2. So we log them. Okay, then we copy and paste. Okay, so we know this is successfully head, right? Then we can copy and this formula down. Okay, so we have to fix the denominator. Okay, so this is 2.7%, this is 2.72%. Okay, so this is I called empirical experiment or empirical test to test theoretical value. Okay, so this is when we apply the formula, we get theoretical value, and when we try different way, this experimental. So when the number of trial increase infinity, our final result should approaching or equal to our theoretical values.
Topic number 3, Poisson distribution. A Poisson distribution or Poisson distributed random variable is often used in estimating the number of occurrence of a specified interval. For example, number of vehicles arriving at a toll booth in 1 hour, number of leaks in 100 miles of pipeline, arrival of phone call within a specified, for example, within 15 minutes time period. Property of a Poisson experiment. The probability of occurrence is the same for any two interval of equal length. For example, for this time period will be the same as next 10 minutes period. The property of occurrence is the same for any two interval of equal length. B. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. To see the Poisson density function, okay, the formula used will be equal Poisson dist. Okay, so this is formula we are going to use. Okay, so let's look at a range from, suppose this is x. So this is density. It's density function. Okay, we have 1, 2, and maybe up to 24. Okay, assume the mean is 10, so we need a parameter 10. Okay, so this is Poisson dist. Okay, so first value is x. Okay, then we have the mean value, and because we are looking at probability density, okay, so this is not cumulative, so it's false. Then we close it. Okay. Before copy and paste, we have to fix the mean, F1. So we hit F4 to log the mean. Okay, then we copy paste. Then we highlight both columns. Click Insert. Click Recommended Charts. So actually this is our Poisson distribution in terms of density. Let's look at a simple example related to the Poisson distribution. Okay, I put two formulas here. Actually, they are identical. Okay, the first one is this is a function. Okay, n is independent variable. It's input variable. Sorry, it's input variables, and lambda is mean, and power is n, and e is exponential value, and lambda is mean. Okay, n is factorial. Okay, and here is use the x instead of n. So n is power n factorial. So if we look at this formula, we know there are two variables, two input variables. One is lambda, it's mean, n is our input variables. Okay, so let's look at this exercise. We are studying the usage of a bank's ATMs late at night. On average, 1.7 customers walk up to the ATM during a 20-minute interval between 10 p.m. to midnight. If we look at here, so 1.7 and 20 minutes, 10 p.m., we have three numbers, 1, 2, 3. Of course, midnight, you can think as 12. For this formula, okay, only 1.7 matter. So what is mean? So mean equals 1.7. Okay, let's make a little bit bigger. Okay, so this is 1.7. Okay, so mean is 1.7. Okay, and also 20 minutes interval. And although this is related to our research, but it's not related to our formula. And also 10 p.m. and 12 a.m. also not related to our formula. Okay, so A, so this is our A, answer A. So B, so B is, and so actually our N equals 4. So our N equals 4. Okay, then what is our probability? So probability will be Poisson DIST, okay, distribution. Okay, the first one is X, so this is X, so actually it's our number 4, and also, and the mean is 1.7, and the last one is 4, because we are not looking at cumulative. Okay, we enter this one. Okay, and so let's use show formula to show our formula. Okay, let's show our formula, make it bigger. Okay, so we use equal Poisson dot dist. So the first value will be x, because this is 4. The second value will be mean. The last one will be 4. Okay, so this is n. So let's look at the C. Okay, the C is what is the probability of 3 or less. Okay, and so this is n. So let's use 3, 2, 1, and 0. Okay, so one way we look at it is simply equal 3, equal 2, equals 1, and 0. We add them together, right? So actually we just apply the formula again. So this is Poisson dist. Okay, so first one is 3. Okay, then we add the mean. We hit F4 and fourth. Okay, we hit fourth. Okay, so this is our, so I'm going to use the show formula. So this is identical to the previous one. Okay, so I'm going to make it bigger. Okay, and so this is 14.9%. So this is Poisson dist. The first one is our x value or n value. The second one will be mean, and this one is false. Okay, then we simply copy and paste. So we copy and paste. Then we copy paste. We got this result. Okay, so finally, so this is our sum. Okay, this is our summation. So equal sum, and we add them together. So we have 90%. Wow, we have 90%. Okay, so according to this formula, okay, so what is the probability of 3 or fewer? Okay, because 3 is 15% for 3, 26% for 2, 31% for 1, and 18% for 0. Okay, so we add them together. So actually, if you really understand so-called cumulative, okay, so let's look at cumulative. So this is Poisson dist. Okay, and so this is 3, and this is our mean. Mean is 1.7. So let's enter true. So true is for cumulative. Okay, it's for cumulative. Okay, so this is a very, very important concept. Okay, so I'm going to use show formula. Show formula. Okay, I'm going to make it bigger. Okay. Okay. So this is 3, 2, 1, 0. We add them together. So we answer question C. What is probability 3 or less? 3 or fewer. Okay. And this is equivalent. We add them together. It's equivalent to cumulatively density function. So this is true. False, we look at individual probability. True is simply we look at cumulative. Okay. And so if we suppose we have 4. And so what is cumulative? So let's copy. We have to log the. So let's just type again. So this is Poisson dist. Okay. So x is 4, period, mean, period, true. Okay, true, 97. Okay. Show formula. Okay, so the meaning of this one is simply is 4 equals 4, 4, 3, 2, 1, 0. Add them together. And if you look at here, actually, so this value should be the summation. So let's make it red. This value should be a summation between equal to purple and purple. Okay, so actually it should be the summation of equal 3 or less plus equal 4. So these two should be same. Okay, I think this example shows us several things, okay? And the first thing is, what is lambda? So this is mean, this is mean. And what is the probability seeing 4 customer? So we only have 1 input variables in addition to the mean, okay? If we calculate individual probability, we use false. If we calculate cumulative probability, we use true.
Shutterstock Music.